be our second in-person SCS colloquium. Welcome everyone, and see you in person is actually really grateful. And today we have the Yueqi Chen from Penn State University. So he's currently a PhD student at Penn State, and while he's actually staying in Chicago because his advisor moved to Northwestern. And he actually received the IBM PhD fellowship in 2002, 2020, and 2022. So actually 3 consecutive years. And then his research work listed in many different places. And then also his approach actually integrated into the internal threat alerting system from JD.com. So welcome our speaker, Yueqi Chen. Here we go.
Okay, thanks. Okay, thank you very much for the warm introduction and welcome. And thank you very much for the invitation, which helps me get rid of the cold weather in Chicago for a couple of days. And I'm very happy to meet with you in person here and share with you my research works and pitch my idea. So at the very beginning, I want to do a little poll. I want to ask you how many shots of vaccination you have received so far. 3, 3, 3, 3, 3. Okay. Oh, 2. Yeah. Okay. So, but I guess you don't want to get another shot. And the reason is very simple because vaccination may have side effect, which makes people suffer. So it's an operating system. In the past decades, we've developed lots of individual patches and individual defenses, and these patches and defenses slow down systems a lot, and users don't know how to configure the kernel in front of so many individual defenses. And despite the efforts, currently the kernel is still under attack. So how to substantially secure the operating system kernel with fewer shots? This is the research topic I want to discuss in today's talk. Oops. People ask a question at the very beginning. Okay. Okay, how about right now? Start your video. Start video. Don't work? It don't work. Oh, here we go. Start video.
Yeah, there it is.
Okay. Yep. Okay. So, I need to. Okay. Yep. So as I said, we've already put a significant efforts on cybersecurity, and basically we rely on 2 approaches. The first approach is to eliminate bugs as many as possible. You know, like software systems and hardware systems inevitably contain bugs, which can be exploited by attackers to launch attack. And the big companies will have bounty programs to invite white hat hackers to report bugs. And one of the most famous bounty program is one from Zero-Team. Zero-Team is willing to pay $2.5 million for an Android exploitation. Apart from bounty programs, we also have developed lots of automated tools to discover bugs. For example, the AFL. AFL will feed a random input to the target program and report it to developers when the program crashes after triggering a bug. And in recent years, many fuzzing tools are developed on the basis of AFL, and these tools are able to find thousands or hundreds of bugs per year. And of course, we have many other techniques to eliminate the bugs as many possible. The second approach to improving cybersecurity is to build defenses to minimize attack impact. For example, the SNAR3, which is a widely used intrusion detection system. It sniffs the networking traffic to detect probes and attacks. And developers also try to harden the software. For example, the Linux kernel, they have a project named the KSPP, Kernel Self-Protection Project, to protect the kernel from attacks. And of course, we have many other protections. According to Gartner, which is a consulting firm, the cost of security and risk management exceeds $150 billion in the past just 1 year. However, the reality is still harsh. According to FBI's report, in the past decade, the number of cyber attack incidents increased 7 times, and total loss increased 27 times. And nowadays, a single bug can generate huge impact, and it's very hard to be patched because the world is more closely connected. In the past 1 year, we experienced SolarWinds attack, which exposed government data and personal information, putting everyone's privacy in risk. We also, and I don't know if you still remember that the price of gas rose significantly in a very short period because of the dark side ransomware. And the Log4j happened just 1 month ago. The attackers was able to launch more than 1.2 million attacks in just 2 days. And nowadays, we're still suffering from this Log4j attack because it will have lots of variants. And it's estimated that it will take several weeks to finally fix this Log4j attack. So obviously, we don't have the confidence to say that the cyberspace is becoming more secure due to our efforts. So what's wrong? Why can't significant efforts bring more secure cybers? Why we are observing more and more attacks despite that we work so hard? Let's take a look into the efforts in the Linux kernel community. When there's a bug reported, it will have a CVE number, and the developers will go to craft a patch to fix this bug and commit it to the kernel. And then another bug is going to be reported, and the developers will go to craft another patch to commit it to the kernel and patch this bug. The patches developed are very specific to the bugs. And sometimes, in addition to patches, we build some defenses, but these defenses are also very specific. For example, to deal with a buffer overflow in 2016, the developers developed a defense named Fortify Source to check the buffer boundary to ensure that the index won't go beyond the buffer boundary. But this defense only works for a very limited set of buffers. So in 2017, in attack, the attackers can still exploit a buffer overflow bug and launch attack to exploit the kernel. To deal with this attack, the developers go to develop another defense named the GCC plugin stack leak. But this defense is also very limited. It only works for the buffer on the stack. Then in 2018, developers noticed that, oh, the previous defense is not a panacea. So we need to have another defense named the static user mode helper to deal with incoming buffer overflow attacks. So based on the previous practice, I can foresee that in the future, we will continue to find new bugs, and we will continue to develop individual patches and defenses for specific security incidents. So it's very like the practice it's very like the race between the virus and the vaccine. At the beginning, we have alpha, we have beta, and we have gamma. And thanks a lot to biologists, we have vaccine for gamma. And in a very short period, here comes delta, and we need to another vaccine for delta. And right now we're at Omicron, and we discover that the previous 2 shots don't work for Omicron, so we need to take a booster. And probably in the future, we'll take a 4th shot for another variant. So you can see that the efforts in the race between virus and the vaccine is very reactive, just like the efforts in the cybersecurity. So can we do better? Can we have a proactive method? Recently, biologists are discussing a universal vaccine. A universal vaccine here is predictable. It works for not only the current virus, but also future variants and potentially other types of coronavirus. In this way, there's no need to take shot for every variant and make people suffer from side effect every time. So I'm thinking if the biologists can develop this universal vaccine, why can't us develop a universal protection for cybersecurity? So how to develop this universal protection? How to have a protection that works for a series of attacks that belong to the same category even before the occurrence of these attacks? My insight is to research attack surfaces. Attack surface is a defect in cyber systems. It could be some, it has another name named exploitable design patterns. It can be some code patterns, can be some data structures that have some common characteristics. Systems developed by different vendors may have the same attack surface. For example, an attack against a heap buffer overflow in the Linux kernel, and another attack against use after free in the Windows system or in the FreeBSD system or in the Mac OS system may misuse the same attack surface to launch attack. If we are able to identify this common attack surface and mitigate it, we're able to develop a universal protection that works against different error types and across different systems. How to realize this? My approach consists of 2 steps. The first step is induction. From a security incident against a heap buffer overflow in the Linux kernel, we're going to summarize the attack surface used in this incident and abstract this attack surface into an abstraction. And with this abstraction in hand, in the second step, which is called deduction, we generalize this attack surface to apply it to different systems across different error types. After the induction and the deduction, the attack surface is no longer specific to one bug or one system, but instead it's a general attack surface. And if we're able to design a protection that can mitigate this general attack surface, we're coming up with a universal protection. So actually, this idea can also map to the race between virus and the vaccine. So like our immune systems have defects, and we may have the same defects. So that's why the same virus and its variants can infect you and also infect me. The biologists will study the alpha to get to know the attack surfaces, get to the common defects in the immune system, and they gave it a name as common dominator. With this common dominator, the biologists can predict other variants like beta, gamma, delta, omicron, and the other emerging variants. Following this idea, I studied in the past 4 years, I studied attack surfaces across different layers of the computer system. I studied attack surfaces in the user space application, attack surfaces in the operating system kernels, and also attack surfaces in the hardware chips. The key techniques that I used include program analysis, programming language, machine learning, and a knowledge of system and architecture. I use program analysis to investigate the program behaviors at the compile time and the runtime. I use programming language, especially specification, to describe and model attack surfaces. I use machine learning to resolve technical challenges in the analysis of the program, and also use the knowledge of system and architecture to build the universal protection in a general approach. Due to the time limit in this talk, I will focus on 2 works, studying attack surfaces in operating system kernels. And additionally, I will describe an ongoing project at IBM, which is to build a defense for the Red Hat kernel. Before I step into more details, do you have any questions? Okay, let me continue. So in the following, I will first describe a security incident against the Linux kernel, and then I will summarize attack surface used in this incident and generalize this attack surface to not only the Linux kernel, but also FreeBSD kernel and the Mac OS kernel. And following this, I will describe the defense that I designed to mitigate the attack surface, and I will give an overview of how this new defense inspired similar mechanisms in the industry. And finally, I will talk about my future directions in the short term and long term. In 2017, a security incident happened against the Linux kernel, and the attacker is able to steal sensitive kernel data like credentials, passwords, and encryption keys from the kernel space. This security incident was reported in Pontoon 2017, and I gave you a background. The Pontoon is a Super Bowl in the hacking world. It offers big prize to attract hackers around the world to show their hacking skills and the techniques. In this security incident, a heap buffer overflow is exploited, and this exploit can affect the kernel version through 4.10.6. And in this attack, a very special data structure is used to launch attack. And the type of this structure is transfer replace state ESN. It's in the networking model. On the slide, I used a green block to represent this data structure. The attacker placed this object right after the overflowed object, and then the attackers place some sensitive data right after this special data structure. This structure is very special because it has a field named bitmap length and another field named bitmap buffer. The size of the bitmap buffer is dynamically determined. So the size of it is recorded in the bitmap length field. After creating this layout, the attacker is going to trigger this heap buffer overflow from the overflowed object and correct the bitmap length field in this special data structure. By triggering the overflow and overwriting the bitmap length field to a large value, the attacker misleads the kernel to believe that the sensitive data is also part of the bitmap buffer. So in other words, in the view of kernel, the sensitive data is also the part of bitmap buffer. Finally, the attacker invokes system calls in the user space and use a kernel function named copy to user to read the content of the buffer. Since the kernel believes that the sensitive data is also part of the buffer, the sensitive data is leaked to user space. And as a result, the attacker is able to steal the sensitive data, steal credentials, passwords, and keys. After this incident was reported, the community took actions very quickly. Unfortunately, these actions are very ad hoc. The first action is very straightforward. They are going to fix this bug and corresponding overflow. Okay. And so that attackers can no longer exploit this bug, this specific bug. The problem of this action is it's very expensive in the production scenario because it requires coordination across different departments and heavy engineering efforts over all buggy products. It takes very long time. And a team leader in a big company once told me that the whole team is only able to fix 13 bugs per year over all buggy products. Another problem of this action is you are encountered with incomplete fix. You can think of the buggy program as a state machine, and we have normal states and buggy states. The normal state is a white ball, and the buggy state is black ball. When a bug is triggered, the program enters the buggy state from a normal state, and then the attackers can use some like this special data structure to transfer the program from one buggy state to another buggy state and to do the exploitation. Incomplete fix means the patch we develop only fix one way to trigger the bug. And the small tweaks of the input can drive the program into to execute another program path and into the same buggy state, and then can continue to do the exploitation. For operating system kernels with millions of lines code, incomplete fix is very common. Even if you try your best to put lots of efforts to ensure the completeness of the patch, you are not safe because a new bug will be discovered in a very short period, and this new bug can be exploited using the same data structure in a very similar way. That is, the attackers can trigger another new bug and put the program into a new buggy state, and then using the same data structure to do the exploitation. So for operating system kernels, which is very large and complicated, finding a new bug is not difficult at all. And actually, according to some measurement works, the rate of introducing new bugs is much higher than the rate of removing bugs from the systems. So this means you can always expect to find new bugs in the system. The second action taken in the community is to randomize the layout of this special data structure. Recall that in the incident, we have a bitmap length field, and we need to ensure that the overflow range can cover this bitmap length field and corrupt this bitmap length field so that the overread can happen. So at the boot time, the developers will try to randomize the layout of the structure by placing this bitmap length field to another offset. So in this way, it's possible that the corruption won't cover the bitmap length field and the attack cannot be conducted. The problem of this action is, first, it's non-trivial to store the random seed. This is because the users need this random seed to build their third-party kernel modules. This means you need to expose this random seed to coordinate users. So a new access control mechanism is needed to support this randomization solution. Another problem of this action is this protection randomization can be easily bypassed using other sensitive data structures. In this diagram, I use this ad to represent this spectral data structure, and the attackers can try to find other structures that have similar semantics to bypass the randomization here. This is because our structures are not randomized, so the exploit can still be successful. So therefore, instead of taking individual actions against the individual incidents, we should take systematic actions by first generalizing this incident. I employed 2 steps towards systematic actions. The first step is to abstract the attack surface in this security incident and generalize this incident across different arrow types and different systems. And the second step is to design a universal protection that can mitigate this attack surface in lightweight and effective approach. By generalization, it means to use the same attack surface implied in the incident to launch more attacks against arrow types and the systems. How to generalize this incident? Let's look more details into this incident. So obviously, in this incident, this structure is the essential attack surface. And this data structure can have some characteristics that can be abstracted. The first characteristic is it has a length field and a buffer field, and the size of the buffer is elastic, is flexible, is dynamically determined. So the size of it is recorded in the bitmap length field. The second characteristic is the content of that buffer can be transferred to user space through some kernel functions like copy to user. And the third characteristic of this structure is it can be allocated on heap. I call this structure as the elastic structure because of the size of the buffer is elastic. So the first step of generalization is to find more elastic structures in different systems. If we cannot find lots of elastic structures in these systems, we can now say like this incident can be generalized and there's no need to build a so-called universal protection. If we are able to find lots of elastic structures in different systems, the second step of generalization is to apply these structures in attacks. If most of the elastic structures cannot be applied in attack, cannot be applied to exploit the bugs in different systems, we can now say like this incident is general and universal. And also there's no need to build so-called universal protection. However, to complete the 2 steps, the 2 steps are both very challenging. The challenges of the first step are twofold. The first challenge is not every structure with an integer field and a buffer field is sensitive. You can easily find lots of structures in the kernel code that has a length field and a buffer field, but a very few of them satisfy the 3 categories that I mentioned in the previous slides. We need to develop techniques to identify these semantics and associate these semantics with the structures. The second challenge is we need to ensure that the structures that we identified can be reached and can be controlled. The structure is just like a diamond hidden in the kernel. And if we want to control it, if we want to operate it in the attack and apply them in attack, we need to execute the kernel. And unlike the user space application, which only has one unified execution entry, the kernel has multiple execution entries. We have interrupts from the peripheral devices. We have exceptions and system calls from user space applications, and the kernel itself will have some kernel threads that do execution. Among all these execution entries, we can only control the system calls during the attack because we need to apply the structures in attack. And also, besides, the attackers is typically an ordinary user. So this means the attackers has no privilege. So we need to ensure that no privilege system call is, we need to ensure that no privilege is needed to use a system call to reach these data structures. Any questions so far? Okay, let me continue. So for the first challenge, which is to identify semantics and associate semantics with the structures, how to find these semantics? My insight is these semantics are expressed in the leaking channels, which are responsible for the communication between user space and the kernel space. I list the leaking channels on the slide, and you can see the function prototypes. And for every function prototype, you have a green argument and a red argument. The green argument is a leaking source, and the red argument is a leaking size. The data referenced by the green argument can be transferred to user space, and the red argument will determine how many data can be transferred. So giving a data structure, if we trace back and discover that the value of the length field can be propagated to the red argument to the leaking size, and the address of the buffer can be propagated to the green argument, the leaking source can conservatively conclude that this structure might be an elected structure. This is because we have a length field, buffer field, and the length field can control the size of the buffer, and it probably can be allocated on heap, and the content of the buffer can be allocated to user space. This satisfies all the characteristics of a elected structure. So what I'm going to do is to do backward analysis from the leaking sites. And during this backward analysis, we collect semantics and identify elected structures. So given the kernel source code, we use LVM infrastructure to compile it into a core graph, which is the structural representation of the kernel. And from this core graph, we find the leaking sites. In the example on the slide, the leaking sites is copy to user. So from copy to user, we'll go backward to see the definition of leaking source and leaking site. U payload is a leaking source. It is defined it is returned from an allocation function, allocation function. And this allocation function is trying to allocate a structure in the type of user key payload. And then we continue to go backward from the bufferlets. And we find that the bufferlets is also a field of the user key payload. So right now, the length field, the leaking source is from the user key payload, and the leaking size is also from the user key payload. And user key payload can be allocated on kernel heap. So it satisfies all the characteristics of a lattice structure. So user key payload is a structure we are searching for. However, statically identified structure doesn't mean that we can reach it during the attack and we can control it during attack. We need a dynamic execution to confirm that they can be reached and controlled. So I set up this environment. I use GCC to compile the kernel source code and instrument the allocation side of this structure and also the dereference side of this structure. And then I run an executor in the user space. This executor will invoke system calls that don't require privilege to the kernel space. And when this unprivileged system calls is able to reach this allocation sites and the reference sites, because we did, the kernel will panic and report. So in this way, we can know that okay, no privilege is needed to reach and operate these elected structures. So how many elected structures do we find in the Linux kernel? I evaluated the static analysis and the dynamic analysis in the Linux kernel, and the results show that there are a large number of elected structures in the kernel. And these structures can cover most general caches in the kernel. So note that the caches here is not the hardware cache, it's a unit of heap management. And covering most general caches means the elected structures are widely used in the Linux kernel. And we also found that no privilege is needed to operate these structures. How about the situation in other OS kernels? The evaluations show that for FreeBSD kernel and Mac OS kernel, the elected structures are commonly implemented in both kernels. And they also cover most general caches and zones. And similarly, no privilege is needed to operate and control these structures. These results show that elastic structures is pervasive not only in the Linux kernel, but also in other commodity OS kernels. And they have the potential to be misused in attacks against different error types in different systems. However, I need to emphasize that it's just a potential. Recall that the generalization consists of 2 steps. The first step is to find more elastic structures, which we have just completed. However, with these structures, we need to find a way to apply them in attacks. If most of the elastic structures that we identified in the previous slides cannot be applied in attack against different error types and different systems, we cannot say that this attack surface is general, this incident is general. So, and there's no need to build a so-called universal protection. And to apply these structures in attack, there are many technical challenges that must be resolved. For example, we need to know the capability, the corruption range and the corruption value of that bug. And we also need to find a way to pair the corruption capability with the elastic structures that we found. And there are also many other techniques, many other technical challenges. Due to the time limit in this talk, I will describe one challenge of applying structures in attack, that is how to reach this desired layout. At the very beginning, the kernel heap is divided into lots of free slots, and these slots are chained into a singly linked list. The attackers will first allocate the overflow object to take over the first free slot, and the elastic structure to take over the second slot, and then the sensitive data to take over the third slot. So it creates a desired layout. And then by triggering the overflow, the elastic structure is corrupted and we can overread the sensitive data. However, this desired layout cannot always be reached. This is because in the runtime, we'll have some noisy objects. The noise is unexpected allocation and free of objects along with the system calls. So recall that if you want to control and operate the elastic structures, we must use system calls and also need other system calls to build up the context in the kernel. And along with these system calls, the system call will also allocate other objects and free other objects, which will ruin this desired layout. So in the real world practice, we can see lots of noisy layouts. For example, we can see a noisy layout separates the sensitive data and the elastic structure. Another noisy layout where the objects separate the elastic structure and the overflow object. And also sometimes we'll encounter with multiple noisy objects. The number of noisy layouts is infinite. It cannot be enumerated. And because the noise is directly depends on the bug, so the noise varies bug by bug. So this means, it's not a good idea to manipulate the heap layout to reach the desired layout case by case, but instead we need to have a systematic solution. The systematic solution is that is giving a set of target objects and a set of target slots. We need to ensure that we can neutralize this noise and put the target object to the corresponding target slot. To deal with this challenge, my key idea is divide and conquer. So at the very beginning, we have a set of target objects and a set of target corresponding slots, and we have lots of noisy objects. And our goal is to put the target object to the target slot. So I developed tools to profile this noisy layout and divide all the noisy layouts into 2 situations. The first situation is the target slot is unoccupied and the target object is allocated to other slot. And the second situation is the target slot is occupied. It is occupied by noisy layout and the target object is squeezed to another slot. I developed algorithms to manipulate 2 situations respectively to create a new layout. And this new layout may still be noisy because we have multiple target objects and multiple target slots. So we need to repeat this profiling and manipulation steps again and again until finally we can reach this desired layout. Due to the time limit, I will skip how to profile the heap layout, and I will elaborate on how to manipulate the two situations respectively. For the first situation, where the target slot is unoccupied, at the very beginning, we have three slots, and they are chained into a singly linked list. And our target slot is the third slot in this list. And we are going to allocate the first noisy object to take over the first slot in this list, and then the free list move upwards to the second slot. And then the target object is allocated to take over the second slot, and the target slot is still in free. So this shows how the first situation happens. The reason behind the first situation is we miss one allocation between the target object and the target and the noisy object. So the solution is very straightforward. That is, I will insert an extra allocation between the noisy object and the target object. So I will use system calls to allocate a dummy object to take over the second slot and consume the free list, and then allocate the target object, which takes over the target slot. For the second situation, where the target slot is occupied, similarly, at the beginning, we have a free list, or have a singly linked list with chains free slots. And in this situation, I will assume that the target slot is the second slot in this list. And the kernel will continuously allocate two noisy objects, which takes over the first slot and the second slot. And right now, the free list refers to the third slot in this list. And we allocate the target object, which takes over the third slot in this list. This shows how the second situation happens, and obviously it's a mirror to the first situation, because the reason behind this noisy layout is there are too many allocations before the target object. So probably we'll think of a mirror solution, which is to free the noisy object before the target object. So in this way, we can put the target object to the second slot in the list. However, I want to point out that this solution is ad hoc. So you still remember that the noise is it depends on the bug. So this means the noise varies bug by bug, and you cannot find a universal way to free the noise objects for all bugs that you encounter in the application of the test. So a more general solution is to reshape the free list. That is, I allocate three dummy objects to consume all the free slots in this list. And then, and still the target slot is the second slot. And then I first free the second dummy objects in this layout. And then right now the free list refers to the second. I free the third slot in this list. So right now it still creates a layout like this. And then I free the first slot. Right now, create a new free list order. With this new free list order, I allocate the first noisy object, which takes over the first slot, second noisy object, which takes over the third slot. And right now, I allocate the target object, which takes over the target slot. After resolving the noise layout challenge, and of course, many other technical challenges, I applied the elected structures to the attacks against the bugs in the Linux kernel. And the bugs that we used for evaluation are very diverse. It's either discovered by the syscaller, which is a fuzzing tool against the kernel, or they have a CV number. And the type of the bugs are very diverse. We have a heap above overflow, we have use after free, and also have double free. And their capabilities are also very diverse. And we apply these bugs to the exploitation, and we achieve the malicious goal of leaking sensitive data, bypassing some kernel defenses, and even arbitrary leaking. The same experiment was conducted over FreeBSD and Mac OS. I applied the elected structures to a very diverse of bugs in both kernels, and the types of these bugs are very diverse. And we also achieve the malicious goals of leaking sensitive kernel data, bypassing defenses, and also even arbitrary leaking. So these results demonstrate that elected structures is a very general attack surface. It can be misused across different error types and in different systems. And so right now it's no longer specific to one bug in one system, but instead it's very general and very dangerous. After generalizing this security incident, the next step towards systematic action is to mitigate this general attack surface using a universal protection. My idea of this protection is very simple but universal. That is to isolate the elected structures. In the attack, the elected structures and the other kernel objects share the same kernel memory region, which is the normal caches. So the corruption stemming from one kernel object will corrupt the sensitive field in this elected structure. So the idea is to put the elected structure to a separated kernel memory region. And this isolation can be conducted in two steps. The first step is at the boot time, in addition to the normal caches, the kernel will create another set of caches, which is called isolation cache. And at runtime, the allocation of the elected structures will be directed to the isolation cache, and the allocation of other kernel objects will go to the normal caches. So in this way, logically, there are war between the two caches, and they never mix up. So the corruption stemming from other kernel objects won't influence the sensitive fields in these elected structures. This protection is very simple but universal. I need to give the credit to the incident generalization because this defense works for all elected structures, not only the one structure that we see in the security incident. And because we have generalized this incident across different error types, so regardless of the error types, this protection can protect the kernel. And also this protection can be easily migrated across different operating system kernels. This, apart from being universal, this protection introduces negligible intrusion to the kernel source code. So that's why in our evaluation we found the overhead is we almost have no overhead. We use 3 benchmarks to test the overhead of this protection. The LM bench is at the granularity of system calls, and the Pharynix will run real-world applications over the hardened operating system kernel. And we also have a customized bench, which will stress test all the operation sites of the elected structures that we identified. The results show that the overhead of this protection is less than 1%. And in comparison, other kernel defenses will slow down the system significantly because it introduces a significant overhead. And the effectiveness of my isolations also evaluated. And in the experiment, we discovered that the isolation can prevent all potential attacks using the elected structures to steal kernel data. I'm very happy to see that this simple but universal protection has inspired similar mechanisms in the industry. The GR Security, which is the best Linux hardening team around the world, extends this protection in their product named AutoSlam. And in iPhone 13 from Apple, they built a new protection named K-alloc to isolate the sensitive structures in the kernel. And currently, I'm working on integrating a more universal protection to the Red Hat kernel. And this protection is more universal because it isolates the corruption rather than the sensitive objects. So in the kernel, apart from the elected structures, we have many other kernel objects that also have sensitive semantics. Although these semantics are different, they all can be used in attack. So instead of isolating the objects category by category, I go directly to isolate the corruption. And since the corruption is isolated and put in a sandbox, they won't influence all the structures that with the sensitive semantics. Let's take an overview of this more universal protection. This protection is it runs an agent in the user space and the BPF program in the kernel space. In many networking papers and products, the BPF program is used to monitor the network and the filter network packets. And here I use BPF program for protection. More specifically, in the user space, the agent will take as an input a cross report. And from this cross report, the agent will try to identify the vulnerable object where the corruption happens. And then the agent will pass this, the type of this vulnerable object to the BPF program in the kernel space. And then the BPF program will intercept all the allocation of this vulnerable object, the allocation of the corruption to the vmalloc region instead of the heap region. So all the kernel objects will be placed in the heap region, and the corruption is isolated in the vmalloc region. So it isolates the corruption. This protection is more proactive because it's able to provide the isolation immediately right after the bug is reported, even before any attacks are launched, because it's end-to-end automation. This means we win attackers in the arms race. And also, this protection is more flexible. It's on-demand protection. It's only comes into being when there is a need, when there is a demand, when there is a bug reported. And for most of the time, it's not enabled, so it won't create any overhead. And this protection is also on the fly. This is because in the real world, probably the machine is running a very important service, and we don't want to stop that service to enforce this isolation. So this protection can provide the isolation on the fly without stopping the machine. Okay, to sum up, in previous slides, I described a security incident against the Linux kernel, and I presented the ad hoc actions taken in the community which don't resolve the problem fundamentally. And then I took 2 steps towards the systematic actions. The first step is to generalize the incident, and the second step is to mitigate the generalized attack surface. Look ahead, I envision that the research over attack surfaces will continue to evolve and become a fundamental part of the software and hardware development cycle. And before elaborating on my future directions, I want to briefly summarize my other research works over attack surfaces. At the application level, my major focus is to improve the quality of security incident report so that the inaccurate information in these reports won't mislead the security analysts. And I also use machine learning techniques to to resolve the memory aliens challenge and accelerate the analysis of this incident. At the hardware level, I design techniques to mitigate the microarchitectural faults caused by out-of-order execution and speculative execution. I mitigated these faults from being used against cryptography libraries. As computer system is evolving very quickly, we are seeing more and more new applications, new infrastructures, and new architectures. And under this new context, we are encountered with new attack surfaces, which require us to develop new techniques to study them. As an example, at the application level, the F-35 pilot used a tablet to communicate with the aircraft. And they use a commercial off-the-shelf product to implement the communication. And this communication presents attack surfaces inside and outside the aircraft. So how to induce the attack surfaces that we studied in other applications to this novel context? This is actually a use case of the DARPA project named Harden. And this project is a $6 million project, and my current group was just awarded this project 3 weeks ago. And since this project is a direct extension of my current work, I will work on this project in the near future. The second example is IoT devices. The IoT devices, their resources are very constrained. They don't have enough computing resource and energy power to support defenses that are widely used in traditional PCs and servers. And also, most of the IoT devices will use real-time systems. So this means lots of tasks in these systems have a time deadline. how to design a lightweight mitigations against the attack surfaces in these IoT devices and without violating the time deadlines is also very challenging, and it's a direction that I plan to go for my future work. And the third example is the novel architecture of GPU. So the architecture of GPU is totally different from the traditional CPU architecture, and there will be new attack surfaces. For example, the attackers can try to manipulate the GPU memory to downgrade the machine learning services running over the GPU, especially the CUDA libraries. So how to induce new attack surfaces implied in this novel architecture of GPU is also very challenging. And as far as I know, there's still no massive research on this direction.
But are you certain that there are elastic surfaces there?
I'm sorry?
Are you certain that there is elasticity, elastic surface? Is that there for the GPUs?
Oh, for the GPU things, actually, I don't know whether they will necessarily have elastic structure, but they will have new attack surfaces. That is totally different from traditional architecture. Yeah, so that's why I need the new techniques.
Thank you.
Yeah. Oh, okay. In the long term, my research goal is to develop an automated cybersecurity reasoning system. And you probably noticed that my previous works still heavily use manual efforts. So why we still need manual efforts? Let me use my CTF experience to illustrate the reason. So this is a photo taken in last year's DEFCON CTF, and this guy is me. So yeah, we have a big team, and but the problem here is everyone has their own domain. For example, I'm an expert in attacking the operating system kernel, and this guy is an expert in attacking the browser, like Chrome browser, Firefox browser. This guy is an expert in architecture, and okay, this guy is an expert in attacking web services. So you see, everyone has their own domain, and sometimes we communicate with each other, but actually we don't totally understand what attack surfaces they are talking about. So we are not using the same language. So the first reason why we still need many efforts is because we are too specific to our own domain. And the second reason is we played CTF a lot. We resolved lots of challenges in the previous competitions, but we cannot easily migrate the exploits that we developed for the previous challenge to the challenges that we are working on right now. The reason for this having many efforts is because we don't have a uniform and formal description of the attack surfaces. So if we have this formal and uniform description, we can describe the attack surfaces in different applications, different things using the same language, and then we also can easily migrate exploits across different challenges. So in the future, I plan to design this cybersecurity reasoning system, and in the key component of this reasoning system is this Lego IR language. I want it to be a domain-specific language that can formally describe all the attack surfaces in these application scenarios. And along with this language, I will have a front end and a set of backends. The front end will take as input a security incident and translate the attack surface behind the incident into this Lego IR language. And we will have a set of backends that will translate this language against to generate the final exploits against the different systems. It works like a traditional compiler that you have a front end which takes as input the source code and generate intermediate representation, and you have a set of backends that can generate the final binary for different architectures. To develop this cybersecurity reasoning system, and lots of techniques are needed. For example, I need the programming language techniques to design this domain-specific language, and in the front-end part and the back-end part, I also need maybe some programming synthesis techniques I also use. And I know that at Boulder, you have a very strong team in programming language, and I really look forward to the collaboration. And also, some machine learning techniques are also needed in this system. For example, in the front end, we can design this technique. That is, you know, that when the attack is when the attacker is trying to attack the system, we can model the change of memory status of the system during attack. We can use the graph to represent all the kernel or the memory objects. In this graph, the node is objects and the edges are the reference relationships between the objects. And along with the execution of the attack, we can have a series of graphs of these memory objects. You can input this these graphs to a neural network and have the neural network to help us to highlight the location where attack surface happens. So in this way, we can reduce human efforts that are involved in the front end part. And I need the knowledge in the system design to design this whole reasoning system and also develop the backends against the different cyber systems. With this cybersecurity reasoning system, we can have lots of application scenarios. For example, we can use this cybersecurity reasoning system to explore the exploitability of bugs in the systems. And with this explore the exploitability, we can generate exploits automatically and migrate exploit automatically. And with this AG techniques, with this automated exploit generation technique, we can prioritize the pattern. For example, say we have an exploit code against a bug in this version of Adobe. This is the version in 2020, and this is the bug at that moment. We take this as input and describe the attack surface in this exploit using this domain-specific language. And with this language, and we can take the newest version of Adobe to generate an exploit code against a newest bug in this newest version of Adobe. And if we're able to automatically generate this exploit, the developers know that, okay, this bug can be exploited. This means this bug is very severe. So we need to patch this bug first. It's very useful in industry because, you know, even big companies like Microsoft and large open source projects like Linux kernel, they don't have enough manpower to patch all the bugs immediately. So the practical practice is to patch the bugs based on the exploitability, based on the severity of the bugs, so that it reduces the probability of being attacked by attackers. Other application scenarios, of course, we can, if we are able to generate exploits, probably we're able to prove unexploitability. That is, give you a bug, give you a system, can you prove to me that this bug cannot be exploited? If this bug cannot be exploited, we need to take care of it, and we can say, okay, we are safe. If we are able to prove these things, I envision that probably we are able to build the scientific foundation of the cybersecurity. And we also can provide guidance for the secure by design. We can also apply this reasoning system to formalize a defense using this using this language. And with this formalization, we can represent all the defense architecture using graphs. And we can quantify the security benefits of these defenses. And with these things, we can optimize the current defenses and reconstruct current defenses. We can also design new defenses with forcible claims. So this means the defenses that we designed can be proved to be effective and can be, we can kind of like rely on them. And of course, we can have many other application scenarios. Finally, I'd like to say thanks to all my great collaborators, and I can never make it without their valuable guidance and visions. And I also want to say thank you very much for attending this talk, and I'd like to open the floor for questions.
Excuse me, I have a question.
Mm-hmm.
I would like to ask, how would the results of this research be different? For example, if we would change the compiler or the compiler version,
Mm-hmm.
how would the results
Okay, let me go back to that page. Okay, so you are asking about GCC things. Let me first answer your question about how the version of GCC will impact the influence idea or influence the results. So for here, it won't influence the results. That is because it's dynamic execution, which means if in the nature it can be executed, can be reached, then in the experiment we can reach it and control it. But for LLVM in the static analysis, the LVM is I mean, we have lots of developers that try. I mean, the development of LVM is very active. So the VLVM will have new versions in a very short period. And in these new versions, the LVM infrastructure will compile the kernel source code using different optimization, compiler optimization and different techniques. So when they generate the core graph, some optimization will be enforced. So the core graph generated every time, generated the changes along with the LVM version. So this means we may have different results if we're using different LVM version. But we find a way to figure it out. That is, when we do this compilation, we're going to hack this LVM infrastructure. We rewrite the generation path of this LVM infrastructure. We disable all the optimization in this LVM infrastructure. So this means the core graph that we generated are totally without any optimization. So no matter what version you are using to generate this core graph, we can ensure that the core graph won't change anymore. Yeah. Please.
When you said the isolation as a mechanism to identify the elastic separate that location.
Mm-hmm.
So how exactly implementation was done, or how exactly identifies to isolate that separation?
Okay, about identification. So this is identification.
Okay.
And about isolation, let me go that page. I guess you are talking about this page, right? Okay, so the isolation, yes, we have already identified all the electric structure in the analysis in the previous slides. And right now at boot time, we're going to create another set of caches at boot time. The kernel will do that thing. And at runtime, when the kernel is going to allocate the electric structures that we identified, we'll instrument a flag. That flag will be passed to the allocation side, to the allocation function. And that flag will specify that this object is the electric structure. It should be allocated in this isolation cache. This is what happened at the isolation time. And when we are going to free this structure, the kernel will use a uniform KPI, uniform interface to free the object. So we needn't worry about the free part.
How much was done? I mean, I wonder because the modification needs to be done during the support needs to be added in boot time.
Mm-hmm.
So how much development effort was spent on that? Because in the beginning you mentioned patches are really hard.
Mm-hmm.
So if this method is very hard enough to adopt, maybe how would it address the original issue itself?
Mm-hmm. Okay, so about implementation thing, the first implementation part is at the boot time, as I said. So that is you are kind of like interrupt the kernel boot time and insert an execution a function. That function will go to create all the isolation cache and have that isolation cache can be referenced by a global structure. That is at boot time, and at runtime. That is you have every object, the allocation of every object will have some flags. So you need to add a flag to this allocation part. That is at boot time. So the implementation is not that heavy. And this implementation can be easily, I would say, easily migrated across different systems. Yes. Yeah, that is the first, wait a moment. That is for this version, but for the next version, okay, for this version is very complicated. It includes, I think, over 5,000 lines of code. So They're very specific to them.
I know the eBPF program should be run in a super user mode, which means the normal user is not really active, but you think someone can manipulate the eBPF space itself, that's actually protecting the report from the generation of the report.
Yes, yes. So that is the key idea of why we need to use a BPF program, because it's able to dynamically intercept some kernel functions and to divert the allocation to vmalloc to other memory region. Yeah. Yes, go ahead.
So this approach is more proactive than the previous one.
Mm.
In this approach, we take the crash report at the runtime, but we're also using some extra space, right? The vmalloc is an extra space that we're using, and that space will only trigger when there's a crash, right? So as soon as you encounter a crash, I wanted to know whether we'll not be using the kernel system calls, like copy to user won't be triggered for using the vmalloc space. How would that go about? Like, say if there's a crash and we know that this elastic structure is causing the crash, so we'll put that elastic structure into vmalloc, right? The runtime. But do we also stop the kernel calls, like the copy to user calls? All those calls will be stopped at that time.
Okay, so for this problem, that is, we are able to isolate the corruption to vmalloc part, but still there is a corruption. So what will happen with this corruption happen? So theoretically, this corruption will penetrate the kernel. And empirically, in our experiment, we found that you can corrupt the vmalloc part because the vmalloc, okay, for two reasons. The first is the vmalloc part is very, very large, it's very huge. It's over 128 gigabytes in the kernel. So some corruption in that place is not a big deal. And the second reason is we do some, more fine granularity isolation. That is, we put the objects of the same type to the same vmalloc bucket. We use the bucket to these things. So all the corruptions are in the same bucket and won't influence other buckets. So in this way, in our experiment, we found that the corruption won't penetrate the kernel. The kernel will still function very, very well.
That means the attack will happen once at least.
Oh, no, attack won't happen.
So not in entirety, but since the crash will happen, the vmalloc will have the object, but still the kernel calls will happen, right?
Okay, so it's like maybe, okay, assume I'm an attacker and I'm trying to exploit this bug, launch attack. And this is because when this bug is reported, this isolation can be enforced immediately. And it's an end-to-end automation, so it can be enforced in 1 second. And if I'm going to launch the attack, right now the isolation is already there. So the vulnerable object is already in the vmalloc part. So I cannot launch attack, but I can cause corruption, but the corruption is not a big deal. It won't panic occur. Yep.
Back to the other isolation. You have your overflow, your elastic structure. Are the overflow structure and the target structure in your experience also elastic? And would they end up in the isolated cache along with?
Yeah, good question. So I guess your question is the overflow object can also be elastic. So when this isolation is enforced, this purple block is also in this part. So you can still to corrupt the sensitive data, right? And but I need to point out that even if this purple part is in here, we still need to have the red part here to complete the exploitation, right? So theoretically, it's possible, and in our experiment, we haven't observed that so far. And actually, we consider this possibility, so that is why we need to have that more universal protection for Red Hat. Yeah. Oh.
So you opened with this idea of comparing security to biology systems using human emissions, not do it against this kind of problem. But there's a big difference, right, between biological systems that are evolving based on the previous generation attacker, adversary, look at your system holistically and decide where they want to choose, where they want to place their effort to attack, right? So I'm curious in this context, given that you're looking at memory disclosure or memory safety issue kernel, and one specific flavor of it with this elastic data structure, do you have a sense of how many are left? Like what fraction of the pie of all memory safety potential issues that could exist in the kernel, does elastic data structures take care of? Does that make sense?
Your question is how the portion of bugs that can be exploited by data structures. Okay, so our experiment. I can only answer this question with the experiment. Okay, so this is Linux bug, and actually the results here is not complete. And the bugs we pick, you can see, yes, I think we have 30 bugs with CV numbers. We randomly pick them. So when we choose bugs for evaluation, we have some criteria. So the first, the bug should be on the kernel heap, and we must be able to reproduce that bug and some other kind of things. But basically, all the bugs that we choose is randomly chosen. And with this random, so in this way, we think that this data set is representative because it's randomly chosen. And with this set, we're still able to launch attack against many bugs. So this means elastic structures can be easily used to launch attack, no matter what type of, no matter the error types and the capability.
I guess I'm curious if you didn't filter this out, if you were thinking more holistically about memory safety generally, how do you have a sense of is elastic data structures the largest problem to solve here? Is it one of 2 problems to solve? Is it one of 10 problems to solve? Right? Because I can think of, if I were an attacker trying to break a kernel that had this kind of solution, I might say, well, I'm going to look for byte code vulnerability.
Yes, you can find another.
Right, and this wouldn't address that. Right? So I'm wondering, how many of these are there left to discover in the sense of thinking about this as inoculating the kernel, or do we just enter a new game of we have an infinite number of shots, they're just bigger shots now?
Okay. Oh, very good question. Very good question. Very good point. Yeah. If you are asking me do we have other attack surfaces? And of course, we do have other attack surfaces. And how many? The exact number of attack surfaces, I don't know. We don't have that ground truth. And your third question is, am I going to create a new game which is still an eternal war? And I would say yes, probably. But I need to say this new game is this battlefield is much more fair than the previous battlefield, because the previous battlefield is we battle against the bugs, and the developers, the defenders want to find every bug in the system, and we patch that bug. Okay, now we are safe. But attackers only need one exploitable bug to launch attack. So it's very unfair, right? But right now we are reasoning about the attack surface, and the attackers is, I'm going to find a brand new attack surface to launch attack. And defender is, you find a new attack surface, and I'm going to mitigate it immediately. And that's it. So this battlefield is much more fair than the battlefield of finding bugs and removing bugs. Yeah. Thanks. Please.
I had a question about what you were talking about at the end, where you were talking about automating exploitation. I guess I was just curious because, I obviously agree that it would be awesome if we could automatically find exploitations, automatically find solutions, and prove that they're unexploitable, blah, blah, blah. But I guess I'm just curious more about the viability of that ideal perfect world. And how would that look different from what already exists? You have an AFL, automatically inputs, random inputs, and see what happens and things like that. I was just curious, what do you think that would look like? I have no idea.
Okay, so the idea is you mentioned about AFL, and the AFL is a tool to find bugs, and it cannot exploit the bug, right? And I'm guessing you are asking a question about the difference between the current tool and the tool I'm going to create.
Yeah, kind of, yeah.
Yes, and let me go that page.
I'm also more just asking, do you really believe in this perfect world where you can automatically do it?
Yes. Okay, so and about this automatic exploit generation things, and I guess you probably know the work from from CMU, from David Blumley. And
I'm a graphics guy.
I'm sorry?
I'm a graphics guy, not a cybersecurity guy, so I'm not.
Okay, and we already have some tools. And my thinking about the AEG thing, about automated exploit generation things is, I think, it's my hunch. I don't have any evidence. This AEG thing is a second order search problem. And previously, we only think of these things we can use some techniques to resolve this. And they have never think about the fundamental thing about this problem. That is second order search problem. So that is why I need to have this security reasoning system. That is, we have this domain-specific language that plays a role as some kind of like template. And to resolve the second order searching problem, that is, we use a template for generation. This is more, I think this is more feasible approach compared with the current, compared with the state of the art.
That's cool.
Okay, yeah, I think it's I like a lot of questions, but if you have more questions, we will stay here for another 10-20 minutes. So feel free to come and talk to the speaker. Thanks again to the speaker. Thanks.
Thanks.